All right, guys, so in this last part of 5.2, our goal is to look at area under a curve. You're going to be able to, first and foremost, put an integral definition together of area under a curve. We are going to take a look at an example in which we relate it to geometry a little bit. And then we're going to take a look at area under a curve, just kind of in a general context of integrals as well, too. So let's dive right in. So we've already kind of talked about this, all right? When we did our MRAM, MRAM, LRAM, RRAM, when we've done that already, we found all of those rectangles, right? We found a bunch of little rectangles. We took added up all the area of all those rectangles, and boom, we got a really good approximation of the area under a particular curve that we were dealing with. And so now we're going to use what we've been starting to unpack of integrals and put area under a curve with a little bit more of an integral definition, okay? So let's say, for instance, that we have a random function. We're going to call it y equals f of x. We have the function y equals f of x. F of x is non-negative and it is integral and integrable, all right? So we can take the integral of it over a random interval. We're going to call that interval a comma b as we have been. We can say that the area under the curve of f of x from a to b is actually equal to the integral from a to b of f of x dx. So that's kind of what we've been leading up to, is that the area under a particular curve, all right, is the integral itself with the lower limit a, upper limit b of f of x, okay? So this is what we are going to use to start finding some evaluations of integrals themselves. So let's take a look here real quick at an example. So at this point, we don't know how to take the integral of any function yet. We'll get there, okay? But so right now, we're going to evaluate this integral with the thought of area under a curve, all right? So let's look at an example. What if we want to evaluate the integral from -2 to 2 of square root of 4 minus x squared? All right, so let's think here for a sec. Area under a curve. That is what this integral's evaluation is going to be. All right, so I'm going to throw a little a here to go along with it, because that's what our goal is, to find the area under this particular curve from -2 to 2. Well, I know that this function itself is a circle. Square root of 4 minus x squared is a circle. And so if I'm taking it from -2 to 2, basically, it's a half circle. So our function represents something like that, okay? Square root of 4 minus x squared is a circle, -2 to 2. That shows me that it's going to be a half circle or a semicircle, all right? And so now let's kind of think for a second. This is a circle. Area of a circle, pi r squared. Area of a semicircle, 1/2 pi r squared. So the area of this figure is 1/2 pi r squared. Well, what's the radius? Well, the center is going to be at 0, 0. The radius is going to be 2, and that means that our area is going to be equal 1/2 of pi times, 2 squared, which is 4. So in this case, 4 times 1/2 is going to be 2 pi. So the area under this curve is 2 pi. Or the evaluation of this integral of square root of 4 minus x squared from -2 to 2 equals 2 pi. All right? So what I want to kind of preface this is when we start actually taking the integrals themselves, you know, we're not going to be necessarily finding area under a curve in this manner. There's going to be some substitution involved and some other rules of integration that are coming into play. But what this does, this gives us a good depiction of what it really means to evaluate an integral itself. All right? So the other thing I want to talk about in terms of area under a curve is what happens if you have multiple curves, right? So let's say, for instance, you find yourself with a function that has a graph that looks, I don't know, of the nature here. Let me expand this out a little bit more. All right, so something of the nature here. Well, you might be thinking to yourself, well, what curve am I taking? Area under the curve. I see a couple curves that are happening in there. In fact, we could sit there and find some rectangles that go through here, and then we could take some rectangles to find the area under this curve here, and then just continue and take some rectangles under this curve here. And so it's kind of trying to think to ourselves is, well, how are we supposed to necessarily get the area under all of those curves? So actually, by definition, it kind of makes some sense. So let's think about it for a sec. We've got an integrable function, y equals f of x. Right? It's got both positive and negative values over an interval, all right, from a to, and then technically, we know about Riemann sums. The Riemann sums for f on the interval from a to b is just simply adding the areas of the rectangle x-axis and then to the negative of areas of rectangles that lie below the x-axis. So kind of thinking about what happens when you do that, the resulting cancellations end up meaning that the limiting value is a number whose magnitude is less than the total area between the curve and the x-axis. So the value really of the integral when it's all said and done is the area above the x-axis minus whatever area is below the x-axis. In other words, we can write this as the integral from a to b. Let's say it's of f of x, because this is our function, a random f of x, okay, of dx is equal to the area above minus the area below. All right, put x-axis here just to make sure we understand. All right, so the area above the axis minus the area that is below the x-axis. All right, and then let's kind of take it one more scenario here. Okay, let's say that I'm only concerned with a function in which all of the values for f are negative. Okay, so let's say if I'm trying to find the area of something that looks more so like this, and I only care about this area that's happening right here because all of these values for f of x in that particular region, a to b, are less than or equal to 0 in this case. Well, if this scenario comes into play, really this is kind of, I don't know, it's almost like the opposite, right? It's the opposite of everything that's happening above the x-axis. And so really, this area is going to be represented as the opposite of a to b of f of x times d of x. All right? And so really, I mean, this is kind of the negative area of f of x, right? Negative area of f of x is kind of what this is looking for. So when you kind of think about this, like I said, it kind of, I don't know, it makes sense. It's common sense, I think, when you think about it. It's going to be under the x-axis. The values are negative for f, and so that's kind of where that negative comes into play there. Okay? All right. So what we're going to do, we're going to take a couple examples here as to how can we dive a little bit farther into integrals themselves in a variety of different ways by thinking of it, like I said, as the area under a curve, okay? So let's start off pretty basic, all right? Let's say, for instance, our goal is to evaluate the integral using areas. That's what our instructions are. Evaluate the area, evaluate the integral using areas here. All right. So we're going to start off Pretty basic here. Pretty basic. We're going to use the function absolute value of x from -2 to 1 of dx. I want to use this one to start it off because it can show a pretty good representation of what this particular function is going to look like. So let's take a look here for a sec. Let's say I draw this function out, absolute value, goes off somewhere in this direction and looks somewhat of this nature. And so basically, from, we'll call this -1, this -2, this +1. So we are curious, kind of, let me highlight this area. So from here to here. So this is the area of our curve that we are concerned with. And so we would make a bunch of these little rectangles that go through here, 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 and here. And that's going to give us our strongest approximation that's going on down, okay? Well, I'll be real with you. To make all of these different rectangles, it gets a little obnoxious, all right? It does get a little obnoxious making all of these different intervals for our rectangles. So what I kind of notice here is that from -2 to 1, that's 3 spaces, or it's a distance of 3 from -2 to 1. 3 different intervals is going to give us a really good idea, if not an exact idea, as to what the evaluation is actually going to look like here. And so we're going to keep it a little simple, and we're going to use the areas that are the intervals that I'm about to mark off here from -2 to -1, from -1 to 0, and then from 0 to 1. So we're going to really look at finding the area of these 3 rectangles, or these 3 intervals specifically. So we have, and just like how we did before, find the area under the curve using our MRAM. So we're going to use MRAM because I think midpoint will give us a little bit better approximation, if not an exact value here. So we have the integral from -2 to -1, the integral from -1 to 0, and we have the integral from 0 to 1. All right, so we have these 3 intervals that we are dealing with. So we're going to use MRAM here, midpoint. So we're going to find the midpoint of each of these 3 intervals. Well, in between -2 and -1 is a -1.5. Between -1 and 0 is going to be -0.5. Then in between 0 and 1 is going to give us 0.5, or half. And so then if you remember correctly, I need to find the height of each of these green boxes that I'm finding. Remember, the height is the y value. So really, I'm trying to find the function, so f of -1.5, f of -0.5, and then f of 0.5. So this is going to give me my 3 heights. So f of -1.5, well, the absolute value of -1.5 is 1.5. Of -0.5 is 0.5. And then of 0.5 itself, of course, will be 0.5 as well. Let me change colors here so I can maybe make these a little bit easier to see. Put this 0.5, make this 0.5, separate these out a little bit with a different color. Okay? All right, so there is our height. Well, now we got to think to ourselves as what is the area? Well, the area of a rectangle is the base times height, or length times width. Well, the base, remember, is the change of x from here to here. So the change of x from -2 to -1, from -1 to 0, and from 0 to 1, that is a change of 1. So that means our width in this case is going to be 1 for everything. So area is going to be 1 times 1.5 for this column, 1 times 0.5 for this column, and 1 times 0.5 for this column. To find the area, it is the sum of all of these 3 areas. So 1.5 plus 1 is 2.5. The area under this curve is 2.5. All right? So it gives us a little bit of insight into how we can use area under a curve. Okay? All right, guys, that is going to this video. I've got one for you to give a shot on your own as we wrap some things on up. I would like you to find the exact same concept, the area under the curve from -1 to 1. The function you are going to be dealing with is 2 minus the absolute value of x dx. And once again, you're going to be finding this area under the curve, and your actual answer to check when you guys are all said and done is 3. All right, guys, on to the next one.